Taylor polynomial and Maclaurin polynomial. Now, what these are doing is creating a polynomial approximation. It's kind of the general idea. So we're trying to get a polynomial approximation to get a value or an estimation for things that we don't readily know. So something like, hey, you know what? What's e squared? I know it's a number. I know it's a decimal, but I don't really know the exact value. Okay, some things like that. Natural logs are another one. What's the natural log of 2? It's not that I don't know. I know it's a number. I'm making a guess at a value, but I don't know that exact value. Right? Now, I know what you're used to doing is you can just type it in your calculator and say, hey, well, this is the ln of 2 or something like that. Well, before you had that calculator, we could approximate it using polynomials. All right, we'll look at some different graphing pieces. So this is a setup for it, and then we'll look at how it's going to mirror the actual function. It doesn't look that great, but it's pretty basic here. Okay, all I want you to focus on is notice the derivative, the power, the factorial. So let's forget about these guys. Second derivative, second power, second factorial. Third derivative, third power, 3 factorial. So what do you think the next one is?
Fourth derivative.
Fourth derivative, fourth power, 4 factorial. Then fifth power. How many terms do you need to be accurate? Infinite. Okay, so an infinite degree polynomial. So this would be what we call a third degree polynomial, because it goes up to the cubic. Okay? But we could create a fourth, a fifth, what have you. Okay? These guys here, right? They look like they're kind of outliers sitting over here. They're really not. It's mirroring the same thing. So watch this. What's the power right here? 1 factorial. So it's really written in the same fashion as these terms. 1, 1, 1. This is no derivative. X to the 0, or x minus c to the 0. 0 factorial, which is 1. So it is following the same pattern on each term. It just kind of looks like it's not. So our Taylor polynomials, we talk about them a few different ways. First off, we call them a degree. So in other words, if I stopped right there, this would be called a third degree Taylor polynomial, just because it went to the third degree. Okay? We can go to whatever degree we want. We also call them by terms. This would be a 1, 2, 3, 4 term Taylor polynomial. Third degree of 4 term. Now, if you think about basic polynomials, just to make one up here, third degree has 4 terms. Because that constant sitting out here, this one's just flipped around the other way where the constant's first counting up. That's the only difference there. All right? They're centered at a value. They're centered at a value, whatever's given. A half, 1, 2, -1, whatever the centered value is. It doesn't matter. Okay? In comes Maclaurin. Says, well, you didn't define it at 0. It's the same polynomial. C just became 0. Instead of x minus c, x minus 0 is x. 0, x minus c is just x because c is 0. Remember how we talked about before Rolle's theorem? Rolle defined it at 0 and got his name in the book. Maclaurin did the same thing. She said, hey, you didn't define that polynomial. Taylor, you didn't define it at 0. I will get my name in the book.
You did.
It worked. So, same thing's happening here. Look. 3, 3, 3, 2, 2, 2, 1, 1, 1, 0, 0, 0. Same thing's happening. The only thing that happens is C. All right, so for you, the general idea would be this. If you're asked to find a Maclaurin polynomial, what you automatically know is that it's centered at 0. You could be asked to find a Taylor polynomial centered at 0, which is just a Maclaurin. Okay? Otherwise, you're given a center amount. Right? So if I'm told to find a Taylor polynomial centered at 2, well, C is going to be 2. Not a big deal. Find a Maclaurin polynomial, I automatically know the C value is 0. There's the difference. As far as that, the setup's the same. And if you can remember this pattern here, so if I had the nth derivative, I have the nth power, I have the nth factorial. So it's really kind of only one term you're really having to remember. It looks like this giant polynomial, memorize the whole thing, but it's repetitive. That kind of help you out. So let's look at a function. Let's go a Taylor polynomial for f of x centered at 1. Let's go a 4th degree. I want to go a 4th degree Taylor centered at 1 for f of x equals ln x. So a 4th degree, if I want the 4th degree, I've got to go to the 4th derivative. Right? So again, remember, 4th degree, 4th derivative, 4 factorial. So I'm going to at least need that derivative. So we're going to start with our initial function. F of x, ln x, f prime of x, 1 over x. And we're going to have to go through to that 4th derivative because we need it for that 4th degree. So f double prime, negative 1 over x squared, triple, 2 over x cubed, 4th, negative 6 over x to the 4th. And check my work there. We agree with those?
Oh, yeah.
Remember, I think of it as power rules. X to negative 1. So you'd have negative 1, x to negative 2. Comes down. Positive 2, x to negative 3. Down. Negative 6, x to negative 4. So now we have our derivatives, but we got to find the values. And we're centered at 1. So let's go f of 1. ln of 1 would be 0. F prime of 1, 1. F double prime at 1, negative 1. Triple prime at 1, 2. And 4th degree at 1, negative 6. Ready, okay there? Okay, now here comes my polynomial. And it doesn't matter what you call it. I'm calling it p of x at p of x over just p for polynomial. It doesn't matter. You can call it f of x if you want. It's not going to change anything. But we're going to have our function value, which in this case would be 0, plus f prime of 1's 1, x minus 1, plus negative 1, and I'll simplify it in a minute, x minus 1 squared, 2 factorial, so we have function value negative 1, the square, 2 factorial. Now we're going to the 3rd degree, our 3rd derivative, so plus 2, x minus 1 cubed, 3 factorial. And our last one, plus negative 6, x minus 1 fourth, 4 factorial. And there's nothing wrong with this setup. I'm just going to kind of get rid of the factorials and simplify it a little bit. So this would then be x minus 1, distribute that 1, minus x minus 1 squared over 2. 2 factorial is 2 times 1, plus 2 times x minus 1 cubed over 6. 3 factorial is 3 times 2 times 1, 6, minus 6 x minus 1 to the 4th over 4 factorial. 4 times 3 is 12, times 2 is 24, times 1 is still 24. And sometimes we'll even see it like this. Let's go x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, because we had fractions we could reduce there. Again, we don't have to, but just see the different forms there. Everybody okay with that? Just reduce those things down. All right, so now after you get that out, get your calculator out.
Wait, so 2 factorial is 2?
2 factorial, yeah, because 2 times 1. We're going to look at some values here with this.
Wait, is it, the reason why it's x minus 1 is it because it's centered at 1?
Yep. Whatever that c value is. So, yeah, so if it was centered at 3, you'd have x minus 3. If it was centered at negative 4, you'd have x plus 4. Whatever that c value is. Gotcha. Okay. Now let's kind of take a look here for a second. What I want you to do, okay, is on your calculators to find p of 1.5. So you're going to put 1.5m for x. So you'd have 1.5 minus 1 minus, I guess this would just be 0.5 squared over 2 plus 0.5 cubed over 3, so on and so forth. I'm just going to rewrite it up here.
Why did you choose 1.5?
Felt like it.
Okay. I was worried that there was some.
No, I just felt like it. I can pick anything I want. I just thought 1.5, nice basic number. I'm trying to get close to 1. Didn't want to get too many decimals. I rounded off, but I got 0.401. Everybody agree with that? Okay. Now, what I want you to look at on your calculator is what is the natural log of 1.5?
Oh my gosh. 0.405.
0.405. Right, okay there, and again, round it off. All right. Are they okay there? Okay, now I want you to go graph. We'll leave those numbers on the board. I want you to go to your graphing, and I want you to graph 2 functions. It doesn't matter which function you graph in the first slot or the second, but we're going to graph this guy. There's one of them. And this guy is the second one, or vice versa. Look at the 2 pictures when they draw.
Interesting.
Let's do this on mine here so I can get the same picture you've got. Now, well, what you see on your calculator probably looks better than what I'm drawing here.
It doesn't.
Something like that. Look pretty similar?
Yeah.
Okay, the perfect drawing. So what we do is graph post. So what we're actually doing is we're creating a polynomial that will mirror the natural log function. Now, it only really mirrored it right in here because that's where it was centered. So if I were to add more terms out here, 5th, 6th, 7th, 8th, 9th, 10th, this black one would transform into that purple one. But how many terms would it take to be the exact same as the purple one? Infinite. Okay, so what it's going to do is going to shift this part of the black one in here. This one will start coming up, and it's going to start following that purple line and mirror it all the way. So we're creating a polynomial that will approximate the natural log function. Now, I know we have computers and things like that, but think back in the day. You want to tell me what natural log of 1.5 is? That's pretty tough.
Yep.
You want to put 1.5 into this and solve it out? All you need is basic functions. You can actually do the decimals by hand if you had to. Okay. So if I selected 1.5, again, I said because I felt like it. I was trying to get something close to 1. Right? Well, here's the 1 right here. As you start moving away, they start splitting. Coming this way, they start splitting. So the further you get from the center, the further you get from accuracy. Does everybody agree with that? But this is pretty close. Now, if I'd gone back and did, say, for example, 1.2 instead of 1.5, these numbers would have been closer. If I would put a 2 in instead of a 1.5, they would go further apart. So the idea that Taylor polynomial or Maclaurin, if it's centered at 0, we're creating a polynomial approximation. All right, so if you're relatively close to the center, it will approximate that value. The more terms that you get, the better the approximation will be. So you got a couple things going on. Closer you get to the center, better the approximation. The more terms you get, the better the approximation. I mean, if I had to stop this at cubic, I would have been a little bit further off here. Graphs wouldn't have mirrored quite as much there. If I'd have went to, say, the 7th power, I would have been closer there on the numbers, and the graphs would have mirrored a little bit more. Does that make sense? Okay. And we can add as many terms as you want. No one's ever going to ask you to do a 15th degree Taylor polynomial. It's one of those things like Euler's method. If you can do a few steps, you can do 500 steps. Okay, so we're not going to get these perfect ones, but as long as you're understanding that the more we do, the better. So we talk about this infinity thing. We did it with Euler's method, Riemann sums, trapezoids. Remember all those things? Where you talk about, hey, we get an approximation, but the more we do, the better the approximation is going to get. Same thing's happening here. Okay. All right, let's switch it now. Let's go with a Maclaurin. I'm going to go with Maclaurin polynomial for f of x equals e to the x. And we'll go a 3rd degree one this time. We did a 4th last time, we'll go a 3rd degree one this time. So when you see those instructions, 2 things you know. If you want a 3rd degree, you're going to have to go to the 3rd derivative. Okay? If it says Maclaurin, where is it centered? 0. Okay? So we could see this written as Taylor centered at 0 or Maclaurin centered. Either way, we know it's 0. So we go 3rd derivative. So I'm going to write my first one. F of x is e to the x. Then I'm going to go 1st derivative, 2nd derivative, 3rd derivative. And the nice thing is these derivatives are all the same in this case. They're still kind of getting this practice writing them out. Notice I'm just listing out my derivatives. Now I'm going to come back, list out my values. We're centered at 0. F of 0 is 1. F prime of 0 is 1. Double prime of 0 is 1. Triple prime of 0 is 1. It's always going to be 1 because it's always e to the x, right? Makes it a little bit easier. So now I'm going to write out my polynomial. P of x. 1, my first term, plus 1x to the first, plus 1x squared over 2 factorial, plus 1x cubed over 3 factorial. And again, this is fine. You can leave it like this, but typically what you'll see, if you look at an answer key, a lot of the ones, of course, are going to be gone, and usually the factorials are worked out. So 1 plus x squared over 2 plus x cubed over 6. Again, you can leave the factorials in. That's up to you. So we're saying that this polynomial graph is similar to e to the x. So e to the x, we don't have to graph this one out on your calculator. So here's e to the x. Kind of know that one. Okay. So this cubic, and I don't know exactly where it is, but what it's doing, it's coming up and mirroring this guy. So something like this. You know what a cubic kind of looks like. And we're getting kind of a mirrored piece right there because that's where it was centered. Okay. And I don't know if that's the exact graph on the purple, but I know it's going to mirror that part. You can graph it on your calculators and kind of see that. It's not going to be mirroring very much because we only went to the 3rd degree, right? What degree do we have to go to make it perfect? Infinite. Okay? And so now the idea was, think about that 1.5 guy again. If you did e to the 1.5 or even like e to the 2, you don't really know what that is without your calculator. But you can find p of 1.5 or p of 2 into that polynomial. So you're getting that polynomial approximation. It's kind of the idea. Everybody okay there? So your goal, whatever this says, get to that derivative. So get your list. Find your values at each one. Then write your polynomial. It's sitting right there for you. You have everything you need. The only thing to be careful of, sometimes you get fooled because it'll say the 3rd term. Well, 3rd term would be the 2nd degree here, wouldn't it? Let's just pay attention. If it says term or degree, it makes a difference there. Okay? It's something we're going to get used to. We'll see quite a few of these going forward. All right.